The use of mixtures of models may involve the calculation of complicated integrals without a closed form. In this video, we provide a brief overview of the concept of Monte Carlo integration that will help calculating these integrals. The name is inspired from a famous casino, and the reason is that in order to calculate an integral, we will rely on random variables. We will basically use chance and random events to approximate this integral. Let's take a simple example. We would like to calculate an integral, which, as you know, is the area under the curve, as depicted in this picture. And as I said, we will rely on random variables to calculate it. Let's consider capital X, a random variable, which has a given probability density function, fx. We define AB, the domain of the random variable. It can be finite or not, it doesn't matter. So let's calculate the expectation of this random variable. And by definition, the expectation is an integral. So this is the integral between A and B of x times the density calculated at x. And actually, you can generalize this definition by considering any transformation of x. So if g is a function from R to R, the expectation of g of x is what? Is the integral from A to B of g of x times the density of x dx. So this is where the idea to use random variables comes from. The expectation of a random variable is actually expressed as an integral. Let's look at this expectation. So we want to calculate an expectation of a transformation of x. One way to calculate an expectation is to use simulation. The idea is that you draw realizations of the random variable x. I denote these realizations by xr, and I take capital R of them. Most of the time we call them draws because we draw from the distribution. And then we calculate the empirical mean of these draws as an approximation to the expectation of the random variable. So the expectation is approximated by the mean, so 1 over R, the sum over R equals 1 to R of gxr. Okay, so I've done two things now. I have, one, expressed the expectation as an integral, which is the definition of the expectation. And then I said I can approximate the expectation using simulation by drawing from the distribution and calculate the empirical mean of the draws. So now I can make the shortcut. If I have an integral, I can consider it as the expectation of something and use this approximation to approximate the value of the integral. This is the idea of Monte Carlo integration. Okay, so the idea is to approximate this integral by the empirical mean of draws from the distribution. Let's take an example. Suppose I would like to calculate the integral of x squared between 0 and 1. Well, in this case, you don't really need Monte Carlo simulation, right? You know the value of this integral. This is 1/3. But let's use this as an example to illustrate Monte Carlo integration. So in this case, the interval is 0, 1, so I integrate between 0 and 1, and I will consider as a random variable a uniform random variable distributed between 0 and 1. So if I consider a uniform random variable, the density is constant, it's equal to 1. And in this case, the g function that I'm considering is equal to x squared. Okay, so if I write this integral here, I have the integral between 0 and 1 of g of x, which is x squared, times f of x, which is 1, dx, which is exactly the integral that I'm looking at. Good. So I have all the ingredients. And now, thanks to simulation, I can calculate this integral even in a spreadsheet. So look at what I have done here. I have opened a spreadsheet, and in the first column, I have generated draws from the random variable. This is called x here. In any spreadsheet, you can have a function that will generate draws from 0, 1. This is what I have generated in the first column. In the second column, I have calculated x squared, which is basically the application of the g function to my draws. And then I have calculated the empirical average of these values. So this one, of course, is equal to this one. This one is the mean of these two, and so on. And this one is the mean of all these values here. Okay? So on this slide, I have done it for capital R equals 10. But of course, I need to continue and put larger value of R. I have continued to do it in my spreadsheet until I've drawn 10,000 draws. Again, you have the same three columns. So this is x squared, and this is the approximation of the expectation of x squared. And as you can see, this is converging to 1/3, which is the theoretical value of this integral. It's converging to it, but it's not exactly equal to 1/3. So this illustrates two things. One, it's extremely easy to do that. I mean, I didn't do anything complex here, right? I draw from x, I calculate a function, and I calculate a mean. And I do it many times. This is the second thing we learned from this, is that it's only an approximation. I've done the same exercise with Python, exactly the same. Before I was using a spreadsheet, now I'm using Python. So this is the first case where I draw 10 rows. I draw from 0, 1. I calculate the square, and I plot this as these dots here. These are the x squared that I've drawn. And then I calculate the mean of this. So this is the approximation of the integral. This is represented by this line. And for a reference, I have put the horizontal line, which corresponds to the theoretical value of 1/3. As you can see with 10 draws, it's a relatively poor approximation of the value of the integral. But as you increase the number of draws, here I have 100, you increase also the precision of the approximation. This is 1,000, 10,000, and here I have removed all the dots because you could not see anything anymore, and 100,000. Actually, the theory tells us that when R goes to infinity, this approximation converges to the true value of the expectation. Of course, in practice, we have no time to wait until infinity. So the question will be, where do we stop? And here there is a trade-off between the computational time, because this takes time to calculate, versus the accuracy of the approximation. So the methodology to apply in Monte Carlo integration is quite simple. We consider the integral as the expectation of a function of a random variable. We generate draws from that random variable. And then we apply the function to the draws before calculating the empirical mean. Okay, now the question is, how do we draw from random variables? That's the key point, okay? So if we are able to do that, the rest is very simple. In the example that I used, we were drawing from a uniform 0, 1. And it's very convenient because every programming language that I know, or every calculation tool that I know, involves a function that generates uniform draws from 0, 1. And here I provide some examples. So this is taken from the MATLAB documentation, Excel documentation, Python documentation. So all these programming languages and tools involve a function that generates draws from a uniform distribution. As we discussed in the context of the example, the density function of the uniform distribution is 1. This is represented by this horizontal line here. And one way to look at this is to see the draws as an approximation of the density function from an histogram. So here I generated 100 draws, and I ask the program to plot the histogram of these draws. As you can see, with 100, I have a relatively poor approximation. But again, as you increase the number of draws, you will see that the histogram will converge to the true value of the density. 1,000, 10,000, and 100,000. And you see that with 100,000 draws, my histogram looks almost the same as the true PDF. Okay, let's now go beyond the uniform. Another typical distribution that we are interested in is the normal distribution. And again, most, if not all, programming languages that I know provide a function that generates draws from a normal distribution. So here I have made the same experiment. So I have drawn from this normal distribution, and I have generated an increasing number of draws. I have plotted the histogram and compared the histogram to the PDF, to the probability distribution function. So you see the probability distribution function of the normal, which is the Gaussian curve represented on this picture, and the histogram for 100 draws. And then I increase 1,000, 10,000, 100,000, 1 million. And as you can see in this picture, with 1 million draws, the histogram is very close to the true PDF. And here the histogram is just a bunch of numbers. We have a list of 1 million numbers, which is easier to handle than the PDF, which may be complex mathematically speaking. Again, I have extracted from the documentations the draws from normal. So this is for MATLAB, for Python, and from Excel. Actually, it is interesting because in Excel, they provide a function to calculate the inverse of the cumulative normal distribution function of a normal distribution. Why do they do that? Well, this brings us to another way to generate draws from various random variables, which is called the inverse transform method. And the idea is the following. So consider the CDF, so now the cumulative distribution function of a random variable, which is represented in red in this picture. It associates every value of x with a probability. So in this case, this value is associated with a probability 0.82 or something like this. The idea of the inverse transform method is that I will use a uniform draw that I can generate from my programming language to generate a value on the y-axis. Okay, I draw from 0, 1, and the y-axis is ranging from 0 to 1. So let's say that I obtain this value here from my random number generator of a uniform distribution, and then I will say that the draw from my target distribution will be actually corresponding to this value. So I use the CDF to evaluate the corresponding value of x, which is associated with this draw from the uniform distribution. So this is very convenient because if you give me the CDF of your preferred random variable, using a uniform draw, I can generate a draw from your distribution. So let's take a concrete example. So suppose that I would like to draw from an exponential distribution with parameter b. So here you have the CDF of this distribution, 1 minus exponential of minus epsilon divided by beta. What I will do, I will write the inverse function of this CDF. And this is minus b times log of 1 minus r. Okay, so if you want to draw from an exponential distribution, you first draw from 0, 1, and you apply this function, and you will get a draw from the exponential. Actually, there is something strange here. Look, I draw from 0, 1, and then I do 1 minus this draw. Well, this is a waste of calculation, right? Because if r is a draw from 0, 1, 1 minus r is also a draw from 0, 1. So actually, there is another way to generate a draw is by putting minus b log of r. For the logistic distribution, so this is the CDF. There are two parameters, a location parameter and a scale parameter. So this is the CDF. So again, a draw from a logistic distribution is obtained by generating a draw from the uniform and then calculating mu minus sigma log of 1 over r minus 1. And the last example that I've used in this slide is to take a power distribution of parameter n and sigma. Again, we inverse this functional form. We draw from 0, 1, and to obtain a draw from the power distribution, we calculate sigma r 1 divided by n. So, we have now a variety of possibilities to generate draws from complex distributions. We have seen that in most programming language, you can do it from the uniform distribution and the normal distribution. And by using this inverse transform method, as soon as you have access to the CDF, the cumulative distribution function of the random variable, and then you can inverse that CDF, you can easily generate a draw from the target distribution. I did the experiment with two examples. So first, I was generating draws from the exponential distribution with parameter 1, and I've used 1000 draws. As for the case of the uniform and the normal, I've done the same. I have generated the draws, and then I have plotted the histogram, and I have plotted the true PDF to compare them. And as you can see, there is a quite good match between the two. And this is the same example for the logistic distribution with 1000 draws. You can see that the histogram is an approximation of the PDF of the logistic distribution. Another technique to obtain draws is to transform them. I take two classical examples here that are useful in practice. That is to draw from a normal distribution which is not 0, 1, and to draw from a log normal. So remember, I told you that the programming languages provide functions to draw from a normal 0, 1. But suppose that you want to draw from a normal of mean mu and variance sigma square. Well, in that case, the way to go is to first draw from a normal 0, 1, multiply by sigma, and shift by mu. And you obtain S, a draw from the normal mu sigma square. Very easy to do. And now, how to draw from a log normal? Well, again, you take a draw from the normal, and the normal mu sigma square, we just saw how to do it before, and you simply take the exponential of this draw, and you obtain a draw from the log normal distribution. Keep in mind that for the log normal, mu and sigma square are the parameters of the underlying normal distribution. They are not the mean and the variance of the log normal. So I have included in this slide the mean and the variance of the log normal for your reference. In this video, we have seen how to approximate an integral with the mean of a random variable. We have seen how to generate draws from different distributions. Now, in the next video, we will investigate the quality of this approximation. We will see also how it can be applied on mixtures of logit models.